In previous video, we have seen what information we get from set of real numbers, but if I say real numbers, our brain automatically think it is a real number line. Real numbers are arranged in a single straight line by the relation greater than. If we take any real number, all of those numbers greater than that number is on right, and all of those numbers lesser than that number is on left. It may look like it only contains numbers like 1, 2, 3, 4, 5, but between each two of those numbers contains uncountably many numbers. But is it necessary for this curve to be straight? Absolute no, because even if it bends, we can still arrange those numbers using greater than relation. As I said before, between any two numbers there are uncountably many numbers. These numbers can be arranged in any manner, so that it obey greater than relation. Here 1.5 must be arranged between 1 and 2, similarly 1.0001 must lie between 1 and 1.5, likewise, others too. And we can join them by straight lines. Adding more numbers between them may produce some weird curve. Now, it may feel like numbers between 1.0001 and 1.2 is much larger than numbers between 1 and 1.0001, because 1.0001 is much closer to 1 than 1.2. So this line must be shorter than that line. But I have opposite here. Because both of these lines has same quantity, they have infinite numbers, but still I say same quantity, meaning I can say counterpart for each number for this line, from that line. Counterpart for 1 is 1.0001. Counterpart for 1.00007 is 1.14003. And so on. Don't be scared by these numbers, I just plug in my numbers in this linear equation. For the x values from this line, we will get y values from that line. Check it. I get this equation by solving the straight line equation for required values. I want x value 1 for y value 1.0001. and x value 1.0001 for y value 1.2. There's nothing but a bijection function from this set to that set. Similarly, we can find bijection for any two finite lines, like sending A to E and B to F, and solve this two-linear equation. This function is a bijective one. We can give counterpart for each number in this line. Also, for each number on that line there is a unique number we can find in this line. This will allow us to replace all numbers with their counterparts. The interesting thing is, if a number is greater than another number, then their respective counterparts will also be like that. We have seen any two lines have same quantity, but for whole real numbers, we had an infinite straight line. It is okay for that curve to be not straight, but is it necessary for that curve must be infinite? That means the curve has no end. No. We can arrange all real numbers in a finite line too. Let me take the line, contains numbers between -1 and 1. I am going to replace these numbers with all real numbers. First, for non-negative real numbers, 0 in place of 0. And replace all others by this. You may guess the function here. I want that function must goes to infinity as x value goes to 1. That's why I put 1 by 1 minus x. Another -1 is for to send 0 to 0, so that we can mirror those function for negative values too. to get the same value for negative numbers. I put absolute value for x. But this will also goes to infinity as x value tends to -1. So I put minus in front, so that this function will goes to negative infinity as x value goes to -1. By this we can define for both negative and positive numbers separately, but we can't define for 1 and -1, because 1 and -1 are for infinity and negative infinity respectively. Infinities are not real numbers, so this function will be bijective on the set of real numbers between 1 and -1, without 1 and -1. Enough from single lines, let's see two lines. One line contains numbers between 0 and 1, other contains 2 and 3. I call it two lines, because it lacks numbers between 1 and 2. Now let's look at a single line again. Can we just break this line at 4? If we want, yes we can, but we want to differentiate that 1 from this. Because if we break this line at 4, one line contains all numbers which is closer to 4 on left, other line contains numbers closer to 4 on right. But there is no actual gap here. That line has missing numbers on the right of 1, so it's illogical to break this line at 4, because neighbors of 4 on left and right are so strong. Let me look through a neighbor of 4, which is 4.00 up to billion zeros 1. This is not equal to 4. But in our real life we can't distinguish these two numbers, we tend to use both the same. There are many neighbors like this for 4, these neighbors define 4 in our real life, so I don't want to break them. In these two lines, we have seen some neighbors very close to 1 are missing in this set. In real numbers itself, every number we see are defined through neighbors. If you point out 0 on real line, that may be 0.00 billion zeros 1, or it may be minus 0.00 billion zeros 1, our brain can't distinguish these two from 0. At closer look, our brain can distinguish 0.1 from 0, but if you take a real line between minus 1 million to 1 million, our brain can't distinguish 0.1 from 0. I bet you even 10 can't be distinguished from 0. Because at any view, we are viewing 0 with the numbers close to them on left and right. At some view 10 can be closer to 0. At another view 0. Billion zeros 1 is no way near to 0, so it's not about some numbers, our neighbors for a number, it's about set of numbers that has enough details about our required number. Now we have seen how we can arrange real numbers, we have an idea about how we are going to view real numbers, we also seen the importance of neighbors to view a set. Neighbors, I mean neighbors for a point in a set. How we are going to say something is neighbors for this point. By a subset, obvious isn't it? Because we are going to define topology on a set, so we are going to use subsets, intersection and unions of subsets, like some basic operations of set theory. Okay, now, what are those conditions? We need to say a subset is a neighbor for a point. Well, obvious one is that point must belongs to that subset. Because those neighbors are going to tell about that point, so that point must belong to that set. And second one is, that set must contain basic points we want to say these are neighbors for this point. For example, in real line, we are seeing a real number through the numbers which very close to them, those numbers are from both left and right. Not just some points on left and right, it must be full stretch to left and right at some extent. Because we can't choose as many numbers from both left, right, and left over this numbers very close to a number, because this set of numbers together define a number. So it is clear that full stretch to both left and right to some extent will give the enough information about that point. How much extent the set stretched is not important. Because if you say it must goes at least for this extent, then it tells us that for each number, there must exist a mandatory number in the neighbours of that number. That's so rubbish. We have seen at point 0 and 10 can be distinguished, but at high view, it looks like 0 and 10 are located at same place. At microscopic view 0 and 0.00001 is far from 0, so it's unfair to say 10 can't belongs to neighbours of 0, and 0.000 must belongs to neighbours of 0. So neighbours are not about some points, it contains points that are going to define our required point. There may be many neighbours, but for each neighbours there must be enough points that defined our required point. You may wonder why we are defining neighbours for already well-placed object like real line, because we are getting information from already defined object. This will give an idea for what would be the necessary axioms for neighbours of our arbitrary set. Let's see another object, a plane. Let me pick a point 1, 1. In real line, a point is viewed through the cluster points on left and right. Is it the same in plane 2, like left and right of 1, 1? No. Because, at normal view, the point 1.001, is very close to 1, 1, but in left-right direction it is no way near to 1, 1. The difference here is, we can travel all direction in a plane. But in a line we can travel by go front, or go back only. So in a plane, neighbours of a point must be from all direction. Also a full stretched in all direction. It may be a circle, or ellipse, or a square. The only required thing is, it must cover all directions. Now we have enough information to define axioms for neighbours on an arbitrary set. Let's define axioms for neighbours. First we need a non-empty set, and a point from that set. We are going to define axioms for this point. As we already know, we need subsets from that set. Let's take some collection of subsets from that set. We don't need all of the subsets of that set, that's why we are going to define axioms on those collection. The first axiom is that point must belongs to all the sets in our collection. Now second one is, every set must contain basic points for this point. Since X is an arbitrary set, we can't say which other points are on left and right or any direction. So first we assume U and V contains basic points for our point. Suppose what happens if the common points of U and V is not a neighbours. It means U tells enough information about our point, V also tells enough information, but their common points doesn't has enough information. So it leads us to U, and V tells different information about our point. It questions the uniqueness of a point. For example, in real line, suppose that line had a hole next to left and right of 0, meaning the line missing numbers very close to 0. Technically it's a real line from -1 billion to 1 billion, removing the points -0.00 up to billion zeros 1 to 0.00 billion zeros 1, with 0 included. The neighbours of 0 may look like -8, 10. Because we are viewing 0 at a distance, even 1 billion can be seen. Since the removed numbers are not visible to our eyes, we can't identify their neighbours, that there are missing numbers. If we ask truth indicator, he will say about missing numbers. But here we are getting motivation, how neighbours are behaving at various look. Okay, back to our view. Here we have neighbours of 0, so it must contain numbers that are going to define 0. Not all the numbers in a neighbour must define 0, since this neighbours contain numbers like 1, 2, 3, 7, -5, -6. This number's not going to define 0 in any way, but still this numbers belongs to our neighbours. Because of this view it look like these numbers are very close to them. But again, if we go deeper, viewing the line from -10,000 to 10,000, these numbers are no way closer to 0. So this is the common points come from previous neighbours to this. Even this neighbors contains many numbers that's not gonna define 0, so let's go deeper. Going deeper in view will let us know that there is a neighbor which contains only 0. Because we already removed these numbers. If we didn't remove these numbers, we will go deeper far and forever. So here 0 works independently, no numbers needed to define 0, because a parent set, we remove the points that's defined 0 previously. So the object we are viewing here is not just a single line, it's 2 lines and a point. It's a subset of real numbers, so it helped us to view their neighbors. Now let's take an arbitrary set containing a BC. We don't know anything about this set. What can be the neighbors for the point A? By first axiom, the neighbor must contain the point A. Suppose A, B is a neighbors for A. We may think B gonna define A. At least B only can define A now. Since C doesn't present in this neighbors. Since every neighbor must contain the basic points that gonna define a point, C can't play any role in defining A. Next, suppose A, C is another neighbors for A. By this, C only has the quality to define A here. Combining these two neighbors, we get to know none of these elements gonna define A, just like we see for 0 in previous example. A is the only common point from both these set. It tells us none of the points can define A. This kind of points are called isolated points. In previous example, 0 is also an isolated point. Now let's look at neighbors of B. Suppose A, B, C is a neighbors of B. Then A and C have the opportunity to become a basic points for B. But if another neighbors has only A and B only, then C lost their opportunity. Now A only can be a basic point of B. If we had another neighbors for A, it may change to let this be like this only. Now for C, if A and C is a neighbors of C, then it will automatically eliminate the opportunity for B. Again, if B and C is another neighbors of C, then obviously C is another isolated points. Because A and B are being dummy in these two neighbors. So the whole set will looks like A and B presented in a single object, where A is isolated inside that object, while C is isolated outside this object. So the knowledge we got from these two examples is, neighbors must contain their basic points. Common points in two neighbors are the important, because it eliminates those points not gonna add any value for basic points. It also tells us these common points contains a basic points. Combining all these two, we get to the conclusion, intersection of two neighbors are also neighbors for the required point. So this is our second axiom. Third axiom is also simple. Because any superset containing a neighbors also a neighbors. Since it also has their basic points. Our goal is to assume the neighbors contains the basic points to define our required point. By imposing these axioms on a collection of subsets, we'll give all kind of neighbors for a single point. But for a whole set, we have to define axioms globally on the set. That's topology. See that in next video.